Computer. Okay, let's hope my laptop doesn't crash. Okay,
so today we are very happy to have Elliot Paquette from McGill University, who will speak about the edge scaling limit of the Gaussian beta ensemble characteristic polynomial. Thank you.
Well, thank you very much for the introduction, and hello everyone. It's nice to see some of you and to see the names of you. So it's a pleasure to give this talk. This is about the characteristic polynomials of random matrices. I'm going to show you a scaling limit of a characteristic polynomial of a random matrix. This is that random matrix. It's in some sense the most classic random matrix that there is. It features as sort of the central object in lots of different theories. This will be connected also to the theory of Gaussian multiplicative chaoses in a way that I'm going to try to explain. But the main object, the way I'm going to frame what I'm talking about is as a new, the description of a new random analytic function, random entire function, which is the stochastic area function. And the stochastic area function appears as the limit, in some sense, of the edge of one of these characteristic polynomials of a random matrix. I've drawn some pictures, I simulated these pictures of that particular stochastic area function. So I would just show you quickly these. Let me, before I leave the first page, just say that everything I'm talking about is joint work with Gauthier Lambert. So these are some pictures of this object. At the moment, I don't have any agenda on what I want you to see in these pictures. This is just some simulations at different values of beta. So for every beta, there's a different random analytic function that appears here. This would correspond to the sort of the edge of where the spectrum, where the eigenvalues form in the plane of this Gaussian beta ensemble. I've done a couple of different simulations. So each of these is a different simulation of the Gaussian of the stochastic area function, and the green line is actually the canonical area function, which is just that nice analytic function defined by power series and a second order differential equation. So there's beta is 1, beta is 2.
What's the red line? There's a green line, a red line, and some other lines.
Yes, thank you for the question. Yeah, the red line is just a particular instance of the stochastic area function. The green line is in fact the area function, and the gray lines are just other independent simulations of the stochastic area function to give some idea of the spread of the random object. These, by the way, are the zeros. The zeros correspond to the eigenvalues of the characteristic polynomial. Sorry, the zeros of the characteristic polynomial, the eigenvalues of the matrix which they describe. The beta functions as a type of temperature parameter, inverse temperature parameter. In particular, as you increase it, the object becomes less random, and you can imagine that as beta goes to infinity, the stochastic area function will become the area function. That is correct. That's how it's set up. So the type of convergence is a little bit strange, maybe. So you can see that the exact mode by which it converges is maybe hard to describe. So here's, for example, beta is equal to 60. Okay. So let me start with just a tiny background to orient ourselves. What is the Gaussian beta ensemble? If all of that was foreign. So it's a distribution. It's a distribution on points. It comes from random matrices, and in some cases, it's actually can be connected to random matrices. So it's a joint distribution on n tuples on the real line, which features two parts. This van der Monde determinant, which is this interaction between the points, and it has a power beta, so the beta is the strength of the interaction. And then also this Gaussian part, hence the Gaussian here, which constrains it to not escape off to infinity, so the points are lying somewhere. There's three particular cases which are important. Beta is 1, 2, 4, and those correspond in those three cases, excuse me, you can actually realize a very canonical random matrix whose eigenvalues follow this distribution by taking symmetric matrices of Gaussians, of independent Gaussians, of equal variance and mean zero. The large n limits of this object are very well understood. Yes, please. Or no question. Okay. The large n limits of this are.
Excuse me. May I?
Yes, sorry.
The O, U, and S were orthogonal, unitary, and?
Symplectic.
Okay.
These will be formed. One way is to make matrices with real entries and symmetric. These are complex entries with Hermitian symmetry in the matrix. And this could be either done by doing a symplectic sort of block structure matrix or actually using quaternions in the entries. You could have Gaussian quaternion entries and then make the thing self-adjoint.
Okay, thanks.
So large n limits of this are pretty well studied. There's a lot of different large n limits and different senses which you can take the large n limits. The first thing is that if you take one of these random matrices, you make n large, you would see a distribution that looks like a semicircle. That's the semicircle is the distribution of the zeros or of the points here. This lambda i's form this type of cloud. There's various ways in which you can form large n limits of it. You can take sort of the fluctuations of the semicircle itself. How far does this curve deviate from the semicircle? That is the histogram. And so if you integrate certain test functions, you can get a central limit theorem. There's also local scalings where you zoom in on the points in a small window. So for example, here, we take some part of the points in the middle and you see some process and you can take n to infinity. And that's a so-called the sine beta process. I only say approximate because this is from a matrix of size 1,000. So as you send 1,000 to infinity, this would converge to the sine process. So that's the bulk scaling limit. There's also an edge scaling limit, which is more closely related to what I'm really going to talk about today. So the points sort of disappear as you get to the edge of the semicircle. And there's a point process that you can get by taking a limit, the so-called Airy beta process. So this is kind of the corner of this universe that is actually going to be what I'm going to talk about. Both of these feature a tridiagonal representation of the matrix. So there will be actually a random matrix that appears in this talk. I'll come to that in a few slides. So the characteristic polynomial, well, if you had a matrix, the characteristic polynomial would be this object, the product of z minus lambda I over all of the eigenvalues. So that's what I'll actually take a limit of today. Why take a limit? Well, there's kind of a large conjecture about this characteristic polynomial, which in some cases has been established. It goes kind of like this. So there's a beta, which functions as a temperature, and then you can introduce another parameter, alpha, and take the characteristic polynomial raised to a power alpha. And if you look at this measure, where you take the characteristic polynomial raised to the alpha, you divide by its expectation, you have what you can view as a random density. And as you send n to infinity, this might converge. The object to which it's converged, or to which it's conjectured to converge, and in some cases proved, is what's called a Gaussian multiplicative chaos, which I'll explain a little bit about just briefly. So this is some random fractal, which can be built from the exponential of a log correlated Gaussian field. And in some situations, there's some success. I won't read all the names, but in particular, when beta is equal to 2, there's some extra structure that you get. And it's actually been shown This whole conjecture has been shown by this group, Clays, Foss, Lambert, and Webb. And there's also work in other related models. The circular ensemble is another class of random matrices, which is a little bit simpler. If this is the first time seeing this, let me just say what this is. So this is really a nice object. It's sort of a class of random measures. There's a particular case where you can see why it should be called a random fractal. So if you choose a very specific case, this is the log normal multiplicative cascade. You can build this as a limit of a type of random Cantor set. And what do? You take a limit of densities and you're going to refine the density on dyadic intervals. So you imagine taking a density which starts at just some level, and then you cut it in half, and you multiply the density on each half by independent log normal random variables. And these are set up to be mean one. So at each step, you're refining by something which keeps the mean the same. If you fix a point, you would see a multiplicative martingale, because you keep multiplying by independent mean one random variables. So you can see this is the type of picture that would result. Mean one martingales tend to go to zero. They go to zero almost surely, but there will be exceptional points where it doesn't go to zero. And so some measure survives in the limit, at least for certain values of gamma. So there's a parameter gamma here. Gamma is the alpha over beta from above. And that gives you this construction of this log normal multiplicative chaos. The GMC is a generalization of this. So it allows for some small amount of difference in that the actual Gaussian field could be a little bit different than the one that generates this one. So specifically, the one that appears in the random matrix setting is more connected to analytic functions, or random analytic functions. Specifically, if you imagine taking this beautiful Gaussian power series, which is just summing complex Gaussian coefficients times z to the k divided by square root k, and take a limit of the ratio of the exponential of this divided by its expectation as n goes to infinity, this is actually the GMC that appears in the random matrix set.
Is it indeed square root k? Not, I mean.
Is it indeed square root k? This square root k is, I'm checking myself. Yes, it's
Square root k.
So that the variance of this grows like logarithm in n.
Okay, I see.
Yes, thank you. So I won't go too much into it, but I'll just say that this has a phase diagram, a non-trivial phase diagram, depending on this gamma. So there's a gamma is equal to 1, and this setup is somehow critical. When gamma is less than 1, this thing exists. It has Hausdorff dimension, positive Hausdorff dimension. The support does. Gamma is equal to 1. There's a critical point. You need to renormalize differently in order to get a non-trivial limit. And there's even a gamma bigger than 1. So you have to start saying what you mean, because this convergence will no longer occur almost surely. Whoops. Okay. So I'm going to leave this GMC. I won't come back to it. What instead I want to talk about, so I do view what I'm doing as in the spirit of trying to answer this question, but it's a relatively long-term project to try to figure out how to do it. In the meantime, what we're trying to do is actually try to say effective ways of describing the characteristic polynomial itself. And what I'll do today is give a specific way of taking a limit of that characteristic polynomial in a neighborhood of the edge. And what has to be done is you have to take the characteristic polynomial, you have to form some kind of scaling in space you have to renormalize it deterministically, since these characteristic polynomials have a huge mean, which just diverges exponentially. You need to renormalize by it. And then what we'll show is that this renormalized characteristic polynomial actually converges to something. And it's very interesting to get the sort of Gaussian field corrections. So if you're interested in proving this type of conjecture up here, the Gaussian field stuff is more what you're interested in, as opposed to the stochastic area function. But in any case, so the stochastic area function itself is what I'm going to focus on. So this is in the edge. There's also a story in the bulk, and I'll try to explain, but in some sense, it can't be done right now. So you have to do the edge problem before you can do the bulk problem. So there is a conjecture for what happens to the characteristic polynomial in the bulk. There's a newly created object by Valko and Vera called the stochastic zeta function. And it's been shown that it is the limit of the circular random matrices, and there's good reason to expect, therefore, that it's the limit of the Gaussian characteristic polynomials.
Where do you evaluate the polynomial in the different conjectures results? Like one is on the unit circle, one is on the real line, or it's, am I confused here?
Oh, exactly. So in the Gaussian beta ensemble setup, if you scale the setup to have the eigenvalues in the limit between -1 and 1, here you'd be looking at ratios of characteristic polynomials, say, at an x, which is inside -1, 1, somewhere properly inside -1, 1, and you form a small 1/n window around it, and you see the stochastic zeta as a limit there. Here we're going at a neighborhood of the edge. So this is 1 in this setup, and we're looking at a window of size n to the -2/3 around 1.
And before it was on the unit circle?
Yeah, and right, thank you. So Valko and Vera proved something on the unit circle for the circular beta ensemble. I should say that, the edge stuff doesn't really have an analog on the circle, whereas the bulk stuff does. Well, the standard edge, I mean, if you do the circular beta ensemble, it has no edge. It just is a nice continuous circle. Okay. All right. So with that, let me try to describe to you what this random analytic function, the stochastic area function. So this is a new object. The stochastic area equation. So this will be the new object. I'm gonna describe it to you. This is the stochastic area equation. It's a second order differential equation with a random term, with a white noise term. So you take two time derivatives in phi, you get t plus lambda phi, and here's your betas. All of your betas are in this √4 of a beta. So you can see it becomes less random as beta grows large. Phi lambda dw. So dwt is white noise. And it is, a priori, you look at this, you say, okay, you have to use stochastic calculus to define this. And in fact, there's a way to remove the stochastic calculus from the picture. There's a way to turn it into just classical calculus with random terms, with Brownian motion terms in it. So it's not truly an SDE. I'll come to that in a moment. So this is the stochastic area equation. If you run it forward in time, it's got a type of divergent behavior. So I've just done 4 pictures here. So this is taking time here and then running it forward. You see, I hope from the pictures, this thing is blowing up, whereas the area function is not. So the green line again is the area function, and the red lines are the simulations of the stochastic, or whatever, the solution of the stochastic area equation from some initial condition. This is a probability 1 picture. So if you take any deterministic initial condition and run the stochastic area equation forward in time, you will not see the stochastic array function, you will not see a bounded solution. You will see something which diverges. So the randomness forces you to pick up perturbations which are unstable and which send you off to infinity. Whereas with the array function, you could, in principle, exactly choose the right initial condition and be on the array curve. On the other hand, if you go backward in time, the stochastic array function is the stable curve. So in these pictures, what I've taken, I've gone to a large positive time, and I've chosen a value, well, close to what the right asymptotic should be. And I've simulated it. So in these pictures, you start to see something which at least looks like it could be a bounded solution. Now you pay a price by doing this in the sense that I've only shown you the picture, from some point in these pictures. This is 4. So I'm only showing you this picture from some level, I don't know, 5. And to the left of it, if you went to the right of it, if you went forward in time, all of these would diverge again. So this is an effective way of giving you a snapshot of stochastic array from some large time backwards. So this is the type of direction you need to use if you want to define a stochastic array function. That's just to come back to where I started. That's a little bit annoying from the point of view of stochastic calculus, because you need to be able to go forward and backward with an equation which has a dw in it. Standard Ito calculus, doesn't like that. You should have adapted things. So going forward and backward could cause problems. Though there is a theory, I think, of how to get around it, and I don't know it. On the other hand, it's also possible to just remove the stochastic array part the dw part entirely. So if you just imagine doing an integration by parts on this, you differentiate these phi's and you integrate these w's. What you can get is you can get an integral equation in dt phi lambda with a Brownian kernel. And Brownian is just as wt, so a continuous function, but it's a continuous random function. And that allows you to see that you have an evolution equation which makes perfect sense going forward in time, backward in time. You can use random initial conditions, no problem. It's all defined. It's all defined with probability 1. So there's no issue with null sets with stochastic calculus building up on you and stuff like that. I did write the equation here, but I don't think I'll show it unless there's overwhelming demand.
But just to understand, so this is the process that the zeros are like the array process or the corresponding array process, or not really?
Exactly, yeah. So this object will have zeros in lambda if you put, well, it actually sort of doesn't matter what you put for t. It will turn out just to shift the process. But this will have zeros in lambda, which are distributed like the array process, array point process. Actually, it turns out the zeros in t are also distributed like an array process, but in a less complete sense. I could try to explain. But it's the zeros in lambda, which are the array process.
Now I am confused because I thought lambda is a fixed parameter and the stochastic equation is in t.
That's right. Absolutely, absolutely. So the evolution here is in t. You have to keep lambda as a parameter. It could be a complex parameter if you like. I haven't defined for you this function yet, so I should need to define some sort of boundary values or something to turn this into a well-defined function. But then, as you vary lambda, this thing will have zeros. So it's a parameter in the equation, and those zeros are the array process. So it's the dynamics are in t. The zeros are in the lambda parameter.
The dynamics are in t, so I get a certain instance, right? I fix lambda, I get a certain instance of this evolution, right?
Exactly.
Okay, and then how do I take zeros in lambda then?
So you would, in principle, you would need to run for each lambda you wish, from some large positive time, you run the equation backwards. You see if you get 0, you try it and try again until you get 0, but it's all on one probability space. And of course, finding other representations which represent this as a function in lambda are interesting. I don't have a particularly good one though. So this is really an equation for defining at each lambda the value of this function.
Okay.
Okay.
Great question.
How smooth is phi as a function of t for the integration by parts?
Yeah, also great question. So this has phi has one classical derivative. Phi lambda is C1. They take one classical derivative, you get a continuous function. You can't take the second derivative. So phi lambda prime or dt phi lambda has Brownian regularity. So if you took another derivative of it, you would need to start talking what you mean.
Okay.
But so this is formulated as an Ito equation, and the phi t dt phi lambda is can be formulated as just an integral equation with a random term. Yeah, thanks. Other question?
Yeah, sorry if this is dumb, but is this something where you can consider t fixed and get a function of lambda? I mean, I'm a bit this SAI thing. You can fix t and get a function of lambda?
Well, so in the end, we will construct a function of lambda, an analytic function of lambda, and it'll be C1 and t, and then actually an entire function in lambda. The description we have is effective for giving the description sort of pointwise in lambda. So finding other ways to describe it, I guess it's just an open question. We do have some things we can say which are locally uniform. So there's some limits where we could take a compact set of lambdas and take a limit and describe it as t goes to infinity, say. But this equation is only effective for describing this at fixed lambdas. That's a great question. I hope my answer was okay.
I'm not at the point where I can really, say if it was or it wasn't. I'm sorry. I'm
Okay.
a little too much of an amateur, but my thanks anyway.
Okay. Well, thanks for the question. Okay, so what's up? So this this is an equation. I've tried to show you that we need to run it backwards in time, whatever it means. We still need to describe what happens. I mean, we need to set some sort of initial conditions or something in order to formulate this as a function and not just as an equation. And to help set that up, I'm going to describe this. I'm going to take the limit to start as beta goes to infinity, because when beta goes to infinity, this is going to go to 0. And what you're going to have is the Airy equation. So if you do that, this is the Airy equation right here. Nice, well-defined classical equation. The standard way of representing its fundamental solutions are as 2 Airy and Berry. And the asymptotics of these as t goes to infinity are well known. The main thing I want to point out is that this Airy solution is the one which decays. It decays like e to the minus 2/3 t to the 3/2, whereas the Berry one is the one which grows like e to the 2/3 t to the 3/2. So you can say from this up to scaling, there's really a unique bounded solution, because if you take any combination of Airy and Berry, you'll get a solution. But if you have any Berry part, it's going to explode as time goes off to infinity. So the only real bounded one is this Airy one. Of course, you have a linear equation, so you can freely rescale it, right? But besides that, you have a unique bounded solution. And this picture is still true for stochastic Airy, and that's going to let us at least extract up to a scaling, up to a random, constant rescaling, the one bounded solution of stochastic Airy. Now we have to prove that there is such a thing. If we have to prove, this type of statement, if we wanted to make that claim, it will work in the end. First of all, this is a two-dimensional linear equation. It has a two-dimensional family of strong solutions if you view it as an Ito equation. And this object could be defined as the unique solution which is bounded. And bounded now means on compact sets of lambda in the complex plane crossed with semi-infinite intervals of time. So that's enough to define it. Now, I have to prove to you that this is actually well-defined statement. I mean, we don't know that you have this picture where you have solutions that grow and that there exists one that's bounded. But this will turn out to be a well-defined object. And that's our first theorem, and I will say a little bit more about it. So this function exists. It's unique, and we will take a convention on what its actual rescaling is. Sorry, what the constant is, if you will, in front of the bounded solution. And we do it basically by understanding the time goes to infinity asymptotics of these solutions. So I've written it here. I suppose that this may just look like a bunch of symbols. I'm trying to show this because of its similarity to the area equation, which has a lot of similarities. So first of all, let me point out there's a Gaussian term here. So this limit is random. This is a very specific stochastic integral in terms of the driving Brownian motion in your process. So we can actually identify it as a specific integral of the Brownian motion. It has a variance which grows like a logarithm, and this starts to bring us back to the log normal random variables and Gaussian multiplicative chaoses. So there's some logarithmic variance term, and there's some constants that depend on 1 over beta. And actually, maybe you would like it more if I rewrite this as that the stochastic area equation is just, the stochastic area function just behaves as the area function multiplied by an exponential of a Gaussian process, and then renormalized by its expectation. I forgot an expectation. That is supposed to be 1/2 the expectation. So this is a mean 1 term. And so actually in mean, stochastic area is the area. And this is an explicit Gaussian function. All right. I'll just say this is set up in such a way that stochastic area should have a limit to the area equation as beta goes to infinity. That's actually beyond what we can prove, but heuristically, it seems clear that this is actually what's happening.
But you mean this is also a process? It is a function of beta as well as lambda and t.
Yeah, it's actually a function of beta, and it's even analytic in the parameter square root 2 over beta. So if you take square root 2 over beta is equal to y, it's analytic in y. I suppose real analytic. I don't know what happens. You could take complex. I have no idea what happens.
So you understand question is like converges, like not pointwise, some process converges or something. That's
I would be hesitant to say it's some kind of almost sure convergence, but it's possible actually. So I would say in law, some sort of maybe law at finite dimensional marginals or something looks like area. Okay. So I'll just do a few properties of this object. Some of these we hit. This is a random entire function in lambda for each t. It's also C1 in t, and its time derivative is Brownian. We hit both of those. There's an invariance in law that this has, and the invariance in law comes from the fact that the white noise which appears in the defining equation is invariant in law. If you shift a white noise, it's just another white noise. And that actually gives rise to a specific invariance in law of the stochastic array function. It's a little bit strange looking, but if you shift by a real parameter the time down by something and shift the lambda up by something for a fixed x, you have the same object. So that's the invariance of law that comes from this. So you actually have that this whole random object for all t's and lambda is the same as this one, where you've shifted the t by x and the lambda by x. So this gives rise to a beautiful picture. I'm going to show it to you. So if you take the zeros, z1, z2, z3, etc., which are functions of t, as the zeros of this map, where lambda maps to the stochastic array function of lambda t, then this collection, zk of t plus t, and it has to be this plus t. So that's, I promise, set up in such a way to respect this this invariance in law property. These are, in fact, an instance of the array point process for any t. There's actually a coupling together of them because you can smoothly change the t, and the z's will change smoothly, and this thing will remain invariant. So you have a stationary coupling of the zeros of the array point process as you vary the parameter t. So just to illustrate this, here are some contour lines of the stochastic array lambda t picture. So the lambda parameter is on the bottom and the t is on the vertical. And I've drawn contour lines at 0. So these should be the array points. These are the gray lines. And you have some other level lines, I don't know what they are anymore, which were positive level lines and negative level lines. So the only thing for which we have any interpretation are the gray lines. And it would be if we fix a value of t, so we draw a horizontal slice, then the places where this horizontal slice crosses the gray lines are an array point process. And you can see that they shift around with sort of a speed, which is exactly t, going down like this, as you take multiple sections of it. So beta is equal to 2 is, in some sense, the most well-studied example. It's the classic one. We could do this for any beta, so I just thought it's interesting to point out what happens when beta is equal to 1. It's the same picture. Things are looking kind of boxy, but these are the these are the level lines. So I had no reason to expect the boxiness. This is just something observed purely in simulation. If you take beta to 0.1, you can see the boxiness seems to be real. It's really getting super boxy. And presumably that means there's a nice limit when beta goes to 0 of the level lines.
You also said, right, that it's an entire function in terms of lambda?
Yeah.
But the zeros are, you only have real zeros, or are there also complex zeros that don't have any meaning?
Only real zeros. Yeah, thanks for the question. Yeah, you only have real zeros, and they look a lot like array, the deterministic array zeros, like to first order any property the array zeros have at a very large scale, these random zeros have. I think it's an interesting question. Just can you take this limit? I wouldn't even know what type of object it is. It might be just that the contours, the level lines, have some limit. It looks a lot like this object called PNG, polynuclear growth, which is a description where you put down Poisson points in the plane, and then you draw some straight lines to connect them. I don't know why it would be standard PNG, which is intensity, which is some function in the plane of Poisson points. So it might be some other intensity points. By the way, just to go back to the comment about analyticity of beta, it was square root 2 over beta, which was the parameter in which this thing was analytic. This is beta to 0, so it's sending that parameter to infinity. I don't know what should happen to it. I guess it's probably too much to ask that there's some analytic function that survives here that has this description. Okay. So I probably should decide now how much more to say. So it's 9:50. I guess I'll go for. I do have a normal ending time, 10 minutes from now or something like that.
Yeah, sorry, I was talking of the mute. Yes, it's flexible. I guess most people would leave at the exact hour, so you can stop whenever you feel comfortable. Then we have some time for questions.
Okay. Thank you. I think I'll probably skip this one. I'll just say briefly what's on the slide and then skip it. The stochastic array function gives a way of diagonalizing what's called the stochastic array operator. The stochastic array operator is a boundary value operator. So there's a stochastic differential operator and boundary values, which allow you to define the array point process. This is the way it was defined in the past. And you can make an explicit connection between this SAI lambda t and that operator in the sense that this gives an explicit diagonalization of that operator. The t here you can think of as the operator, the parameter over which you're taking derivatives. And so these are eigenvectors in T of that operator. Let me actually formulate a theorem showing the convergence of the characteristic polynomial to the stochastic array function. I'll probably stop there. So so far I've told you that the stochastic array function exists, and I claim that it has something to do with the characteristic polynomial, and now I just want to say what that is. So the mathematical tool that makes all of this connection possible is that the Gaussian beta ensemble has a representation in terms of a determinant of some Jacobi matrix, random Jacobi matrix. So this A matrix is infinite, and it has normal random variables on the diagonal. It has high distributed random variables on the off diagonal. And if you take a finite submatrix, an n by n submatrix, and form the determinant of it, this is a monic polynomial, and it's actually equal in law to the characteristic polynomial of a G beta E, of a Gaussian beta ensemble. So this is an explicit way of representing the characteristic polynomials of Gaussian beta. So as a determinant, as a characteristic polynomial of this tridiagonal matrix. Now, if you want to show convergence to stochastic array, what we do, is you can embed this matrix into a Brownian motion in some sense. If you take the A's That was the entry on the diagonal. It's a normally distributed variable. Those are easy to embed in Brownian motion. If you take the y's, those were the ones, sorry, the b's. The b's are the ones on the off diagonal. They were chi's. So you can recenter them and you can rescale them. And now you have mean 0, variance 1 random variables. And there's this magical coupling, which allows you to say that, okay, the Hungarian or the KMT coupling, which allows you to say that these sums, partial sums of these random variables can be coupled in such a way that they're close to two independent Brownian motions. So x's and y's are independent random variables. We're going to take two Brownian motions in such a way that these sums are close. That's the probability space on which we work. And in that probability space, we can do all of the stochastic analysis. And we can actually give a theorem, which is an explicit coupling between the two things, between the stochastic Airy function and the Gaussian characteristic polynomial with some error bound. There's quite a lot of notation on here. I think what I'll point out maybe a few things here is that you can write the recurrence. This is a tridiagonal matrix, and the determinants, the characteristic polynomials of them, have a nice 3-term recurrence. It's random because the Jacobi matrix is random, and you can embed that 3-term recurrence in this kind of matrix representation. If you just take the random parts and you set them to 0, or equivalently, you take expectation, then you can see this this recurrence that you see over on the right pane. And this actually is a very well-known recurrence. It's the recurrence that defines Hermite polynomials appropriately. You have a Gaussian measure, you take expectation of the characteristic polynomial, you get the Hermite recurrence. And those are known to converge to the Airy function in the neighborhood of the edge. You have to divide by some factor. And so we take the exact factor that you need to get an Airy recurrence, or to get an Airy equation, so to get the Airy function from the Hermite polynomials, which is this sort of heinous looking thing. And we're going to use it in the random setting. So we do that, and we define psi n hat to be phi n times this wn, whatever it is, and we scale space appropriately. And then what has been observed before, and which was the basis for the starting of the Airy point process, is that this 3-term recurrence starts to look like the Airy equation. So if you just rewrite it, you can see that you have I guess you'll have to trust me that you see a discrete Laplacian term appearing here. And discrete Laplacian, so this is in time. And it is then forced by this t plus lambda times psi n term, and then in fact a random term, and the random term is built from x's and y's, which were the random entries here. And this, if you put it all together, is how you end up with the Airy equation, with the stochastic Airy equation. You get two time derivatives is t plus lambda psi, and then if you combine these two sources of noise, you get some dw, some sort of combined total noise, which is coming from both of them. There's also discretization errors, and you can quantify them, and there's also coupling errors, which are how far away these noise terms are from the dw. They're all relatively small, and they're going to stay small throughout the whole story. In the end, they're just going to remain small. So the main task is actually to show exactly that you can basically neglect these errors, that they don't propagate and they don't explode and cease, to have an Airy function, a stochastic Airy function. And this is the type of quantitative statement we can do. We can actually take this deterministically rescaled characteristic polynomial, which is the psi hat, and we can say that uniformly on compact sets of time. So time, I'm thinking with the t space as the lambda. And for any number of derivatives in lambda, this psi is given by some Gaussian stuff. And there's sort of two Gaussian terms, a stochastic area function and a vanishing error, an n to the minus 1/6 error. And in fact, all of these errors are vanishingly small with overwhelming probability. So all at once, from the start, overwhelming probability is smaller than any power of n. In some sense, you only have n bits of randomness in this problem because you took an n by n matrix with n IID random, well, n independent random variables. And now we're talking about events of probability less than powers of n at any power of n. In some sense, you'll never find typically any deviation here. So you can take union bounds, you can take a mesh over the whole space, and you can apply this bound everywhere.
Where are the derivatives coming into the picture? It says for any number of derivatives in lambda, but I don't see where derivatives in lambda are coming in.
So these errors remain uniform if I take here d lambda on both sides, and it would be d lambda here. This has no lambda difference.
You can take derivatives of this equation and it'll remain valid with the same error.
Yes,
okay.
Exactly. Thank you. Yeah. And this actually has one corollary, which I'll just point out. This was coming from a problem that was arising in spin classes, that there was a question about can you say if the modulus of the characteristic polynomial at the edge is independent of its zeros? And in some sense you can, because in this picture, there's this Gaussian, and it's big. Its variance 2/3 log n. It overwhelmingly determines the modulus of this object. Everything else here is sort of not even competitive. This thing is a bounded object. This thing is a log n object, variance log n object, and this thing is a variance log n object. And this g, that's a g. If anyone asks, that's a g. This g is independent of the stochastic area function. So this determines the modulus if you rescale, and this determines the zeros. They're actually independent of each other. So that's what's written here. Okay, I'm happy to talk more about that or to answer any questions. I'll scroll down and end. Here's some summary. There's lots of open questions about properties, about limits, about going into the bulk, about various things. But in any case, thank you for your attention.
Thank you very much, Elliot, for the nice talk. Any questions?
You have, right? You said you have an analytic function of lambda.
Yes.
So you can look at the, I mean, you can expand as a power series, look at the coefficients one by one, right? Ask for their distribution.
That's a great question. Yeah, I don't know if we have anything about it. So you would maybe fix a time and look at, say, maybe since the value, the distribution of stochastic area at a fixed lambda at time 0 is a complicated object, but you could maybe look at the joint distribution of it and its derivative, or maybe the log derivative, remove the complicated part. And I don't think we even know the tail properties of it. I think there's some sense that it should probably be relatively heavy tailed. Because if you look at time is equal to 0, stochastic area lambda can have zeros. The derivative could be big, and probably the tails have something to do with beta, also with the noise parameter. But I don't think we know anything about it, except for that they exist.
Okay, thanks.
In the definition of operator, there was some function f 0 in 0 and ensemble of class, but how it was related with operator, it's on something wasn't written.
Yeah, thanks for the question. So the operator, there's a operator, a stochastic area operator. I'll find it. Sorry if I'm giving you seasickness. Here we go.
Yes.
So it's set with some, it's a Sturm-Liouville problem effectively, but it's on an infinite interval. And the standard setup, the one that gives the Airy beta point process, is that you set the value of your function to be 0. You also specify that it's in some sort of boundedness class. So in this case, I put W12. So in some sense, effectively setting its value at infinity to be 0 also. And then the eigenvalues of this on that space. And again, there's a way to turn this into a non-Ito derivative. You can do an integration by parts. The eigenvalues of this are the Airy point process up to a change of time. They might be the negatives of it. The SAI lambda, if you fix, so this is this bullet here. If you fix, say, t, you can fix any value t, so t is equal to 0. And you look at the zeros of SAI lambda 0. So they're the zeros in lambda of this SAI random entire function at a fixed t is equal to 0. Those are the zk. And this is an eigenvector of this. And it's an eigenvector of this because, well, it's 0 at 0, so it has the Dirichlet boundary condition. It decays. Its derivative is in L2. Its derivative is in any LP. And it's actually a complete family of eigenvectors of that operator. There's even things you could do where you change this boundary condition, and they have interpretations which are nice. Did I answer the question?
Thank you.
Okay.
If I understand correctly, the picture that you gave for the sort of the limiting differential operator, it's also true for the bar, right? So there is some technical difficulty in justifying it.
Sorry. So in the book, there will be, you can look at, say, the ratio of the characteristic polynomial at the point divided by a fixed base point and try to get convergence. The way that the stochastic, the recurrence is set up, if you want to do that problem, at least from the point of view of taking the recurrence of the characteristic polynomials and taking a limit, what happens is that you have different regimes of the recurrence, and there's a part where you get the bulk behavior, the oscillatory behavior that gives the stochastic zeta function. But you also have a region where you have you have sort of 3 regimes of behavior of the recurrence, and you have to do all 3 of them to answer the problem. There's too much information on this slide, sorry, but so the point is that you actually have to do this version of the problem, the so-called hyperbolic problem, the parabolic problem, which is the one we just did, and then you have to do the elliptic problem. So we've done 2 of the 3, and they build off one another. So it's rather that you use what we did as input if you want to do the stochastic zeta function limit. I think it really has a different, it's kind of a different problem which uses this as a sort of initial condition as an input. Though we wonder if the stochastic Airy function, the classical Airy function becomes just a cosine, right? If you go in the oscillatory direction, it's oscillating more and more, it becomes more and more like a cosine. And presumably the stochastic Airy function becomes, if you took a limit of it, the characteristic polynomial in the bulk. So that's one of our questions. If you send lambda to -infinity, do you get the stochastic zeta function of Valko and Theorem? Which would sort of answer the question of the characteristic polynomial being stochastic zeta, but it's a sort of different scaling limit.
But like at the non-rigorous level, if you don't care about, if you want like a physics type proof, then you can derive it in the same way, I guess, if I understand correctly what.
Yeah, I think so. Yeah, you could, right. I think you could heuristically write down why it should become the stochastic zeta function. Though, so you know, this is a second order differential equation, and the stochastic zeta function is a first order stochastic equation. Not that that's the end of the world. I mean, such a thing could happen as you take a limit, but you're losing smoothness, so you have to work out exactly how this limit occurs. But I think it would actually be a nice just probability problem just to show that if they have some sort of weak convergence or any type of convergence of the stochastic area function to stochastic zeta. I don't know how it goes, even at the physics level.
Sorry, and what were lambda plus and lambda minus, which you mentioned before? Lambda plus and lambda minus, what is it?
Was I talking about this one?
Yes.
So the recurrence for the characteristic polynomials actually looks like a perturbation of a deterministic recurrence, which is the one where you just take expectation of those of that recurrence. This 2x2 matrix, as you vary little n, as you vary z, as you vary its parameters, will undergo a transition in terms of the type of eigenvalues it has. And that greatly affects the type of how the perturbed equation looks. So in the regime where you have one eigenvalue bigger, two real eigenvalues and one bigger than the other, it's sort of a scalar recurrence. The stochastic area equation results from the regime where the two eigenvalues are about the same. So you're sort of degenerate. And the stochastic zeta function, the behavior of the sign process, the bulk scaling limit, results from where the two eigenvalues are complex conjugate pairs. And you have a macroscopic rotation. So it's a very wild recurrence.
Thank you.
Oh, thanks for the question.
Sorry for disappearing for a while, but
I understand.
Questions. So thank you very much, Elliot.
Okay, thank you.
And thank you all.
Nice to see you. Thanks for your attention, everyone. Have a wonderful day.
Did you have to wake up very early, Elliot, for this?
No, I didn't have to wake up very early, but I did wake up. And I thought to do something else. I was going to go out. I was going to go running. I was going to do something. And I was going to be here at 10, which would have been about right now. And I'm really glad that didn't happen. For some reason, I thought to myself, I should check what time it is in Israel. and then I had 15 minutes to get ready. So, so no, it worked out very fortuitously. Yeah. I suppose I could have been in.
The time differences are very confusing. Yes.
Yeah, no, it's like addition.
Addition is very confusing.
It's an unknown quantity. How
I guess,
the
Oren, you
kids?
can stop the recording.
That's a good point.